The atoms of any object that is spinning are still moving. Thus, they must have some kinetic energy. So consider here, we're going to take this wind tunnel or whatever, wind turbine, but I'm really just going to talk about two little masses that are attached to it and are spinning around. So right now we're not talking about the energy of the entire turbine, but just the energy associated with these two little like blobs or whatever that have been put on the edge of the, along the edges of the blades here, on the blades. And the kinetic energy of particle 1, of course, would be m1v1 squared, 1/2 m1v1 squared, and the kinetic energy of particle 2, of course, would be 1/2 m2v2 squared. But of course, these linear speeds, v1 and v2, are connected to the angular speed by the thing that we had just talked about, that v1 and v2 are going to be omega times the radius r1 or r2. Right? And so far I've said nothing but just that I can replace these linear velocities with their angular, with something they're equal to by their angular motion. But here's the crux of the matter. For a rigid object, the omega is the same for all the atoms. So I can call it just omega as I did, and I can do some grunchy, stupid little algebra here, and I can say, well, the kinetic energy is then going to be 1/2 m1v1 square plus 1/2 m2v2 square. I can make my direct substitutions, 1/2 m1 times the quantity, omega r1 square, plus 1/2 m2 times the square of the quantity, omega r2. Do out the stupid algebra to get the omega square r squares, and then factor it. And I'm going to do it in kind of a weird way, but I'm going to pull the half out front, and I'm going to pull the omega square out back. So I'm going to take this and move this to the front, but I'm going to take omega square and I'm going to move it out to the back. And the reason for doing that is that now I get a form, which is that the kinetic energy is 1/2 times some constant, something, times omega squared. The something here is called the rotational inertia, and we get something called the rotational kinetic energy. All right? We've replaced, it's like a kinetic energy, which is 1/2 mv squared, to remind you, hopefully redundantly, that the kinetic energy has been 1/2 mv square, and we've now turned that into an equivalent looking thing, which is 1/2 times something times a speed squared. So that's why we call that the rotational inertia. It's acting like the inertia factor did in regular kinetic energy. We'll talk more about that rotational inertia term in a little bit, so if you're waiting for it eagerly, hold on and we'll get there. Be careful with this. This rotational kinetic energy is not a new form of energy. It's just plain old kinetic energy. We've just written it in a more convenient form. Instead of tracking both particles, we've now just tracked their combined thing. For 2 things, it's probably not that helpful. For 3, it'd be better. But you can certainly imagine if talking about an actual object made of real atoms, we have 10 to the 23 or so of these things. It's much nicer to just take it as one number instead of the sum of 10 to the 23 of them. To distinguish from what we studied earlier, the older or usual kinetic energy is now called translational kinetic energy. Translation being things moving along a line, as opposed to rotation, things moving around a circle. And if the axis of rotation is moving, like for instance for a rolling wheel, then the object would have both of these things. It has some translation of the center of mass plus some rotational energy associated with spinning about that point. As said, the constant proportionality between the kinetic energy and 1/2 the speed squared is called the moment of inertia in the old school usage, or the rotational inertia in a more modern usage. We symbolize it by the letter I, and it's measured in units of kilogram meter squared. A couple of things. One, you might wonder why this? Like, why would you have that extra little factor in there? And that really is because we'd like this to look like the kinetic energy is 1/2 an inertia term times the speed squared. So we're trying to make it look like the earlier one, and so we have that extra factor half pulled outside. We'll find out later that that half is the same half we've been running into all year. When we talk about the dynamics of this thing, the rotational inertia will be defined in terms of the equivalent of forces and won't have the extra half in there, and you'll see that it'll all be consistent. But right now, just take it as sort of, it will be convenient that we factor out the half first. Also, as a really quick aside, everybody says it's symbolized by the letter I, capital I, that I've written there. I'll say that too. almost certainly we'll see later this is probably really supposed to be Greek letter iota, but the Greek letter iota when capitalized looks exactly like the Roman letter I when capitalized, and so no one respects that. All right, you can see that I plays the same role for rotational motion that M does for translational motion. That is, when two objects have the same rotational speed, there's more energy of motion associated with the object that has a larger rotational inertia. Later we'll see this analogy is even stronger, and I acts like M in terms of dynamics. How hard something is to spin depends on its rotational inertia. It is harder to twist something with a high I than with a low I, and so on. That will come back in a little while, though. Right now we can just say it's also that they carry more. Something with higher rotational inertia carries more energy for a given speed. Falling back on how we define this, we can say that for a single point particle m located at a distance r from an axis of rotation, the rotational inertia is mr squared. And again, while memorization is not the key to this class, you absolutely want to know this one offhand and cold, that for a single point particle, the rotational inertia is just its mass times its distance squared. It's weird. It looks a little bit like center of mass stuff, mass times position, but it's position squared, and we'll come back and see why that is. But mostly at this moment, it's just that algebraically convenient to do it that way. If there are multiple point particles all rotating around the same axis, and that's kind of important, then we would simply add their individual rotational inertias, which is what we did before. The inertia of many point particles is just m1r1 square plus m2r2 square plus and so on, so on, so on, which is often written in math speak by using the Greek letters capital sigma to say sigma of mi ri square, where the I runs over all the possible things, 1, 2, 3, 4, etc. If the point object's not a point particle, well, things get complicated, and we'll get back to this in a little bit. So, an example. 3 heavy marbles are glued securely to a lightweight disk as shown. The point of saying all those things is that the marbles can be considered to be point-like. All right, they're heavy, and they're essentially, since they're small, they're basically point-like. And the disk is lightweight, meaning it's essentially massless and does not come in, which is good because we haven't talked about how to handle things like disks, which are extended objects. So really we're saying we've got 3 point particles rotating around. And the question asks us to say, circle in blue the letter or letters of the disk or disks with the greatest rotational inertia, and circle in red the letters of the disk with the least rotational inertia. Give it a go. So remember, we fall back on that for any 1 point particle, for any 1 point particle, it's mr square, and then we add them if there are multiple ones. So let's take A as our reference, and let's make a couple of conceits here. Let's say that this is some distance r, and this is almost zero-ish. So our base one here might be mr squared, but there are 3 of them. So that's sort of our base to compare to. For B, it's going to be approximately 0. They're almost all at the origin. It's going to be their mass times some very small distance, which we then square. And so certainly compared to A, that's nothing. For C, it gets a little interesting. We can still say this is basically R, and that is basically R, but the other guy is at 0, and so we get mr square plus mr square plus 0, or 2mr square. So it's already lost out to A, and it's more than B. So C isn't going to get either kind of circle. Also, we can immediately say B being 0 has to get the least. All right. And then D looks a lot like C, so you might be tempted to say, oh, it's the same thing, but we have to be careful because this dot is our rotating axis. So this circle is doing, this guy is doing that circle, and this guy is doing that circle, which is kind of crazy, but we can handle. All right, and can't seem to erase them, don't know why. So we'll go up here. So then we have, for the first one, it might be 0, because this guy is at the origin, so r equals 0. And then this guy pulls up mr square. But this one pulls up m2r squared. And if we look at that, that's mr squared plus 4mr squared, or 5mr squared, meaning this is way more even than A. So this guy gets the blue circle. All right, about which axis is the rotational inertia greater, where the bars are massless? So again, we're talking about essentially point masses being held in space by empty things. And our key thing is to keep track of where our rotations are. And in case B, it's relatively easy. This is our axis of rotation, so everybody is moving like this. Oops. What happened? Moving around like that. But for case A, it's a little weirder because you have to sort of imagine the whole thing coming out of the page and then going back in. I have to probably better do that. So like this, and then around again. So you have to imagine the thing spinning out of the page. All right, so we can look here and say, well, first of all, M1 is contributing nothing in either case. It's 0 from the axis, so we have M0 squared, or 0. Duh. And then M2 is contributing the same amount to both, because it's the same distance from both axes. So it's going to contribute M2 R2, right? Yeah. In both cases. So it all comes down to what happens with this third one. And now we can see that in case A, the radius is smaller than in case B. And so M3R3 squared is going to be smaller there than it is here. So when we add them, will also be smaller. And so we end up with that B is going to have the same. If you want to see the actual stuff worked out with numbers, you can grind out here. The book I stole it from decided they wanted to compute stuff. But do notice, as indicated before, this didn't contribute to either of them, and this contributed the same to them. So the only difference was because of these two. And it turns out, kind of maybe interestingly, a factor of 2, which is the square root 2 squared, which is interesting.